Hi, welcome to this video about dynamical heat transfer. My name is Karl-Erik Hagentoft. I work at the Chalmers University of Technology in Gothenburg, Sweden. This picture shows the problem we are looking at. It's a body that stores heat and it's thermally insulated in the surroundings. So the red area symbolizes the solid or the fluid body, and which has a volume V, a mass M, an exposed area A, density rho, C is the heat capacity, and the starting temperature. And we'll assume that the temperature is uniform within this body. And we would like to estimate or calculate the temperature, how it changed in time. The yellow area symbolizes the thermally insulated wall with the thickness D, and the thermal conductivity, lambda, is all. And the surrounding temperature is TE. And this diagram shows how the temperature is changing in time, and at time 0 we have T start, and in beginning we have big temperature difference between the body and the surroundings, so we can expect quite big temperature difference during a certain time, while it will diminish a bit when the time is increasing and the temperature difference between the body and the surrounding is not so big anymore. And soon, after some time, the temperatures will go down to the ambient temperature. Let's put it into formulas. P here symbolizes the heat loss from the body, and it is determined by the temperature difference, the lambda value, the thickness of insulation, and the exposed area. And during a small time interval, dt, we'll lose a certain amount of heat, energy, and that is coupled to the heat capacity and the change in the temperature, D, capital T. And we put these together in the equation here and change the order a bit of the terms. We get this term in front of the temperature part here, temperature difference. And from a dimension analysis, we can see directly that T here and T there has the same dimension, and so we got to have T here in the denominator. So we define a time scale, Tc, which is given by this expression here, and that will give a time scale of the problem. If we are solving the ordinary differential equation we saw on the last slide, we get this solution. So it's an exponential decay, starting at the start temperature, and slowly but surely the temperature is reaching the surrounding body, the surrounding temperature. And to understand how long things are taking and couple it to this characteristic time, so if we have e exponential up to -1 here, which is roughly 0.37, we can see that 63% of the temperature has been reached at this characteristic time, and there's still 37% left of the total temperature drop at this time. Let's look at an example. Let's say we have a freezer that stops working. We have a temperature of -20 degrees when it happens. The freezer has a shape of the shoebox, 0.5 meter times 2 times 1 meter. We have the 5 centimeters of insulation with the thermal conductivity 0.03. And we have 20 kilograms of ice inside the box, and the surrounding temperature 20 degrees. If we look at the heat capacity for ice and for water, they're different. It's the highest values for water. And since we're also reaching the melting of the ice, since the surrounding temperature is above 0 degrees C, we also have to look at the latent heat, which is given here also. So the characteristic time when we have ice is 2.9 hours, and when we have water it is 5.54 hours. And during the time the ice is melting, the temperature difference is constant 20 degrees, so we can write down an equation easily how long time it takes to melt. So the effect, which is constant during this time, times the time, is equal to the change in the latent heat, which is m times L here in the formula, and that is actually 22.1 hours. And here is a diagram for the whole period. So we have starting at minus 20 degrees. We have an exponential increase here up to trying to reach 20 degrees, but it stops here at 0, and when the ice starts melting, and we have these 22 hours of melting, and then another 5-6 hours before it roughly reaches the ambient temperature. We'll also look at the propagation of heat into a thick wall. We have a step change in the surface temperature, so at time 0 we have a sudden increase in the temperature with the amount of T step. The thermal properties of the solid is important, and we have the thermal conductivity lambda, the heat capacity, and the density is important as well. Here we see in animation how the temperature and the heat is moving into the object. After half an hour, 1 hour, 2 hours, 4 hours, 8 hours, 16 hours. We see now it's reaching further into the material, into the solid. And this problem has actually a solution as well. It's written down here. So we have a special function called the error function, RFC, complementary error function. And we don't have to know so much about it at the moment, but it has these values from 0 going to the infinity. So the error function's value, complementary error function's value is between 0 and 1. And we see that the argument here inside the function S is equal to the depth in the solid and divided by square root of 4AT. And A is the thermal diffusivity of the material in the solid, and it's equal to lambda divided by rho C. And if we look at the values here, starting with, if we put in x equal to 0, the argument for the RFC of the function is 1. We will also get the same value if t is equal to infinity. And we put into the formula, we find that the temperature is equal to the new temperature, the new after the change. This is of course correct at the boundary because we forced it to be the new temperature at the boundary. But also for a very, very long time after infinity, we have reached the new temperature in the whole solid. And error function, the complementary error function is around 0.5 for the argument 0.5. That means that we reached half the total change at that when the argument is 0.5. And if we go to very deep into material or at the start of the process, when we have t equal to 0 in the denominator or x equal to infinity deep down into the material, we see that we have the starting temperature everywhere at that time. We can find out that when the argument is 0.5, we roughly have half the change what happens into the material. And this is a very important finding. So we can say that the position of the heat front, when we have had this half change of the total change, we call it x 50%, is actually equal to square root of A times T. And if we manipulate the formula a bit, we can say at a certain position x, it takes T 50% time equal to x squared divided by A, when before we find it had reached the 50% change. An example here, rho C is 10 up to 6, lambda value 1, the thermal diffusivity 10 up to minus 6, starting temperature 10, the new temperature 20 degrees. And we know that the moving front in the simulation is like square root of AT. The time it takes for the front to reach 0.3 meters into the material using the formula is around 25 hours. More exactly 27.48 hours, but roughly 25 hours. Now we see a simulation of how the temperature front is moving into, this 50% front is moving into the material. On the vertical axis we have the temperature, We see the temperature in the whole object is the blue line, and the red front is moving forward. This is the 50% change position. Now the simulation has been 16 hours, 17 hours, and it soon reaches the point 0.3, the depth of 0.3 meters into the material. And if everything is working correctly, it should take around 25 or exactly 27 hours. You see it goes slower and slower. Start in the beginning, it goes quite fast, and it goes slower and slower. And there we go, 27 hours we have reached, or that's an approximation, 25 hours. We can also look at seasonal temperature variations in the ground. We know that we have a warm season and a cold season, so the temperature at the ground surface is changing from winter to summer, back and forth, back and forth. And there are some simple rules for that as well, how deep this disturbance goes down into the ground. And it's well known that the temperature is rather constant if we dig down into a well or into the caves of deep into the soil. And the depth can be calculated in the same fashion as for the step change we just analyzed. We had this x 50% was equal to square root of 8t. We can get a similar one, like a 37% reduction of the amplitude. So the amplitude is 37% of what we have here. This is the amplitude at the ground surface, and down here at a certain depth, x 37%, the amplitude has been reduced to 37% of what we have up in the at the ground surface. For regular soils, it's 2 to 4 meters, and we have this formula for x 37. So it's thermal diffusivity times the time period, and for these seasonal variation, the time period is 1 year, and divided by pi and take square root of that, and we get actually the penetration depth, the periodic penetration depth for this type of variations. Now we look at the simulation of this periodic variation. And on the left hand side we see the temperature, and on the horizontal axis is the depth into the ground, for instance, in this case, and we see how the temperature in the ground is varying from summer to winter. Now we're reaching the summer here, the warm period here at the summertime, and we go down in fall and reaches the winter periods here, and it goes up and down like this here at the surfaces. And we can see how the propagation of the change is diminishing the deeper we go into the material. And we have some conclusions. We have established formula for the time scale for a body of fluid or solid with uniform time temperature, Tc, given by this formula. We have found that the thermal diffusivity is an important parameter for the propagation of heat in material. Found that we have a formula for the position of the temperature front due to step change at the surface of a thick wall. We also established a formula for the time it takes at a certain depth x to reach a 50% change, and penetration depth due to periodic variation of the thick wall or ground. Thank you.